Wildfires are a serious economical and environmental concern, and understanding their causes is crucial for prevention and mitigation. A question raised by policymakers could then be, to what extent do environmental variables like temperature and humidity influence the risk of wildfires? For example, we might expect that the higher the humidity in the air, the lower the fire risk on that day. Similarly, we expect that high temperature increases the risk of fire. To answer this question quantitatively, we use real-world data that captures key environmental factors such as daily temperature and humidity and wildfire occurrence. The policymaker might ask, is there a consistent relationship between environmental variables and fire risk? This can be seen from a mathematical point of view. Find a model that predicts the risk of fire based on temperature or humidity. This curve will be our model. Among different possible models, we will introduce linear regression to determine linear relationship between variables. The key question is now, how can I construct this line mathematically? Thanks to its easy interpretability, linear regression is a popular statistical technique used to model relationship between an independent variable x and a dependent variable y. This technique assumes that the relationship between variables is described by the equation y equal m times x plus q, and the coefficients m and q have clear and intuitive meanings. Specifically, q represents the y-intercept, that is, the value predicted when x is equal to 0. M, instead, represents the slope of the line, that is, the rate of change of y with respect to x. Or in other words, if the independent variable x increases by a certain amount, delta x, the predicted dependent variable y will change by m times delta x. Let us now see how we can find a line from a cloud of points. We know that for two distinct points there is exactly one line that passes through them, but what happens if there are many points? Well, in this case, there are many lines that pass through pairs of points, but none of them perfectly represents all the points in our data set. So how can we choose the most representative line? Well, the idea is to associate to each line a score, and then we select a line with the lowest score. Let's see how we can compute this score. Let x1, y1 be the first point, x2, y2 be the second, and so on for all n points. For a given point, x, y, we define y hat as the predicted value from the model, that is, m times x plus q. The difference y minus y hat is called the residual, and it measures the error between the actual and the predicted value. Our objective is to find a line that minimizes these residuals, making the difference between observed data and model predictions as small as possible. More precisely, we look for the line that minimizes the sum of the squares of these residuals, that we denote by E. E is our score that quantifies the total error between observed and predicted data. By varying m and q, we obtain different line, and for each combination of m and q, we can compute the corresponding score E, which, as we said, is the sum of square residuals. Out of the infinitely many lines generated by changing m and q, we will select the one that minimizes E. And this will be our mathematical definition of best fitting line. This approach is known as least square regression, as it focuses on minimizing the squares of the residuals. Now, to find the values of m and q, we must ensure that the partial derivatives of E with respect to m and q are equal to 0. That is to say that no further improvement is possible. By performing the necessary calculations, we find that the coefficients satisfying these conditions are given by these formulas. We need a computer code to perform these operations automatically, and in the upcoming videos we will explore how we can implement these formulas in Python and in MATLAB.